This video contains the solutions to the practice problems for double integrals over rectangular regions. So here we have an iterated integral that we want to evaluate. And remember that what this really means is that we want to integrate the inner integral with respect to y, treating x like a constant. And then we'll evaluate the outer integral, just like we would an integral back in Calc 1. So if we want to integrate 4xy with respect to y, remember the 4x is going to be a constant. So that integral is just going to be 1/2 y squared multiplied by that constant multiple 4x. We'll evaluate that from y equals 1 to y equals 4, and then whatever we get from doing that, we will integrate that with respect to x. So plugging in y equals 4 and y equals 1 gives us 4x. When we plug in 4, we get 4 squared, which is 16, times 1/2, which is 8. And then 4x times 1/2 times 1 squared, which is just 1/2. 4 times 8 is 32, so that's 32x minus 2x, which is 30x. Integral of 30x is 15x squared. We evaluate that from 0 to 2. That's going to give us 15 times 4, which is 60. So that's the value of this double integral. Once again, we have an iterated integral, and again, the idea is that we want to evaluate this inner integral with respect to x, and then evaluate the result with respect to y. This time we have to work a little bit harder because we have x times the cosine of xy, and if you remember your techniques of integration, here we're going to need integration by parts. Remember that when we pick our u and our dv, we want to pick a u that gets nicer when we take its derivative, and a dv that doesn't get too much nastier when we take its antiderivative. So again, remembering how this works, we let u equal x, and dv is going to be the cosine of xy. Du is the derivative of x, which is dx. V is the antiderivative of cosine of xy. And again, this is tricky, but think of y as a constant, and so the antiderivative of cosine of xy, if that's hard to think about, just go off on the side and figure out the cosine of, let's say, 5x, right? And again, how that would look is the antiderivative of the cosine of 5x would be 1/5 sine of 5x plus or constant. And so with the y in there, we're just going to get 1 over y times the sine of xy. And again, remember when we do integration by parts, we don't need the plus c. So we get the integral from 0 to pi. So we get u times v, which is x times 1 over y times the sine of xy, minus the integral of v du. So the v is going to be 1 over y times the sine of xy, and the du is just going to be dx. So continuing, we get x over y times the sine of xy. Now the antiderivative of 1 over y sine of xy, remember the y is a constant, so that 1 over y out front is going to stay there. And then when we take the antiderivative of sine of xy, we're going to get another factor of 1 over y, and then the antiderivative of sine is cosine. So cosine of xy, and then remember, now we're evaluating from the x goes from 0 to 1. So we're going to plug in x equals 0 and x equals 1. When we plug in x equals 1, we get 1 over y times the sine of y. This is going to be plus 1 over y squared times the cosine of y. And then when we plug in 0, the first term is just 0, and the second term is going to be 1 over y squared times the cosine of 0. And then that's what we have to integrate with respect to y. But we're going to run into a problem here, because integrating sine of y over y and cosine of y over y squared, both of those are very difficult integrals that we don't really have good techniques to evaluate. So we've done all this work, and we get stuck at this point. So it turns out that what we really should have done, and again, it takes some practice to learn to recognize this, what we should have done is reverse the order of integration. And since we have a rectangular region here, we can just switch the order of the two integrals, and we switch the order of the dy and the dx. Now we can evaluate the inner integral with respect to y, and now we don't need integration by parts, because now the x that's sitting out front of that cosine is just a constant multiple. And even better, the x is exactly what we need to make the substitution u equals xy work. If I'm thinking about u equals xy, then du is just going to be x dy. Remember, I'm integrating with respect to y, so that derivative that I'm taking to do the substitution is also a partial derivative with respect to y. And so this x that I have here is exactly the factor of x that I need to make the substitution work. So the antiderivative of x cosine xy is just sine of xy, evaluated from 0 to pi. Plug in pi, plug in 0, I get sine of pi x, and then sine of 0 is just 0. So this is just the antiderivative of sine of pi x with respect to x. And then when I take the antiderivative, I get negative 1 over pi cosine of pi x, evaluated from 0 to 1. When we plug in 1, we get cosine of pi times 1. Minus a minus is a plus, 1 over pi times the cosine of 0. Cosine of pi is negative 1, so that's 1 over pi, plus another 1 over pi gives us 2 over pi. So that's not that hard of a double integral, but we have to realize that we need to switch the order of integration to make it easier. We're going to see a couple more examples of this later on in this same worksheet, but really keep your eye out for, would this integral be easier if I switched the order? Okay, so this time we're given a rectangular region. We're given that this is, x is going to go from 1 to 2, so when we look at this first interval, that's my x values, and the second interval, that's my y values. So now the question is, how do we set up the iterated integral? There's two ways to do it. We can put the x values first and the y values second, in which case we're integrating with respect to y in the inner integral and x in the outer integral. Or we can put the y values first and the x values second. We're still integrating the same function, but this time we would be integrating with respect to x first and y second. Now this time the function is relatively simple, x squared plus xy. I'm not going to need integration by parts or substitution or anything fancy for either one of these. So both of these ways of doing the integral are probably going to be equally difficult or easy depending on how you think about it. So let's just do it the first way. So we start by integrating with respect to y. So the antiderivative of x squared is x squared y. That's the integral of a constant. And the antiderivative of xy is going to be 1/2 x y squared. And then we plug in minus 1 and 1 and subtract. When we plug in 1, we get x squared plus 1/2 x. Minus what we get when we plug in negative 1, we're going to get negative x squared. And then negative 1 squared is positive 1, so we get plus another 1/2 x. So this 1/2 x cancels out with that 1/2 x. And so I just get the integral from 1 to 2 of 2x squared dx. That antiderivative is 2/3 x cubed. Plug in 2, plug in 1, and subtract. We get 2/3 times 8 minus 2/3 times 1. That's going to be 14/3. So as a practice problem, I encourage you to work through this other integral. You should get the same answer. It should be 14/3 no matter how you set up the order of integration. So that's a good practice problem to try on your own to make sure you get the same result. So here's what we're really leading up to. So when we have a function, we have to decide what the order of integration should be, and very often it's easier one way than it is the other way. So how are we going to decide whether we want to do this integral of this function, 2y e to the 4xy? Do we want to integrate that with respect to x first, or do we want to integrate it with respect to y first? So think about what you would have to do to integrate it with respect to x versus with respect to y. Notice that we have a y sitting out front and a y in our exponent. So the only way we could even hope to approach that integral is by doing it by parts. And we want to try to avoid integration by parts if we can, right? It's just like back in Calc 1 where we tried to avoid the quotient rule whenever we could. Since we have a choice, the person giving us this problem doesn't care how we do it, they just want the volume. So it doesn't matter which way we do it, we just want to try to do it the way that gives us the easiest integrals to do. So since there's only a single x, we're not going to need integration by parts if we integrate with respect to x first. So we're going to want to set up our integral with dx on the inside and dy on the outside. So my function is 2y e to the 4xy. That means I need to put the x numbers on the inner integral and the y numbers on the outer integral. And I integrate with respect to x first. I'm going to need to do a substitution, u equals 4xy. My du is going to be 4y dx. Remember, that's going to be a partial derivative with respect to x. So I need a 4y. I've got a 2y, so I can make that be a 4y by multiplying by another factor of 2 and putting a 1/2 out front. Just like I would have done back in Calc 1. It just looks a little weird because I've got x's and y's. So I'm integrating from 0 to natural log of 2. I've got a 1/2. And my antiderivative is going to be e to the 4xy, because the antiderivative of e to the u is e to the u. Plug in 0, plug in 2, and subtract. Remember that I'm plugging those numbers in for x, not y. So I have 1/2 e to the 8y minus 1/2 e to the 0. Remember that e to the 0 is not 0, it's 1, so don't get that wrong. So we've got 1/2 e to the 8y minus 1/2. Antiderivative of 1/2 e to the 8y is going to be 1/16 e to the 8y. Antiderivative of 1/2 is 1/2 y. Plug in natural log of 2, plug in 0. So when we plug in natural log of 2, we get 1/16 e to the 8 times the natural log of 2 minus 1/2 times the natural log of 2 minus what we get when we plug in 0, which is going to be 1/16 e to the 0 minus 1/2 times 0, which is just going to be 0. So that's 0. E to the 8 natural log of 2, that's 2 to the 8th. Then we multiply that by 1/16, that's going to work out to be 16. So it's going to be 16 minus 1/2 natural log of 2. E to the 0 is 1, so it's going to be 16 minus 1/2 natural log of 2 minus 1/16. That's going to be 255 divided by 16 minus 1/2 natural log of 2. Now this time I can't encourage you to try the integral the other way and see if you get the same answer, because it actually turns out to be very difficult to do the integral the other way. So that's sort of the point of this problem, is helping you learn how to identify the easier way to do the integral. Last one, and this is another one of those same problems where we have to identify the easier way to do the integral. Again, dead giveaway here is that we've got an x out front and we've got an x inside the secant squared. So integrating with respect to x would require some kind of integration by parts. So since we only have a single y, we're going to integrate with respect to y first. That means that the inner integral is a dy integral, which means we put the y values on the inner integral. And so we get x times the secant squared of xy dy dx. Again, we're going to do a substitution, u equals xy. Since we're integrating with respect to y, this derivative is a partial derivative with respect to y. So that's going to be x dy. And hey, isn't that convenient? We happen to have a factor of x here to make that substitution work. So that's really just the secant squared of u, and the antiderivative of secant squared of u is tan of u. So that's the tangent of xy, evaluated from 0 to 1. Remember, we're plugging those values in for y. So when we plug in 1, we get the tangent of x. And when we plug in 0, we get the tangent of 0, which is 0. So this is just the integral from 0 to pi over 4 of the tangent of x. Now you may remember that the antiderivative of tangent of x is negative natural log of absolute value of cosine of x. Now if you don't remember that, then what you would have to do is rewrite tangent as sine over cosine and do a u equals cosine x substitution. But if you just happen to remember, and hopefully you do, that the antiderivative of tangent is negative natural log of cosine, then you're good to go. So at this point you may need to go back to your Calc 1 earlier in the book, a lot of the Calc 1 facts and some of the Calc 2 facts, integration by parts and so on, just to refresh your memory on some of the integration stuff that you definitely knew at some point, but maybe have forgotten by now. But now I got to plug in pi over 4 and 0. So I've got the natural log of cosine of pi over 4, minus a minus is a plus, natural log of cosine of 0. Cosine of pi over 4 is square root of 2 over 2, so that's negative natural log of radical 2 over 2. And then cosine of 0 is 1, so that's the natural log of 1. But the natural log of 1 is 0, so this is just negative the natural log of square root of 2 over 2. Or if you want to get fancy and simplify it, it's just the natural log of the square root of 2. Of course, if you left it as negative natural log of radical 2 over 2, that's perfectly fine.